All right, welcome to Lecture 6. We're going to be doing more stuff on lists and also comparing lists to tuples. So we're in Python. Let's do a simple list where we have L equals, and this is just a really simple list with just three values. And they're not sorted. And we've done things like we've changed values inside a list. So we can say list with a subscript, let's say of 1 equals 8. And now if we print the list, we'll see that we've got 182. Okay, that's good. Now I've shown you before that there's this other thing called a tuple. And I'm probably going to introduce you to a new word today called mutable or immutable. Lists are mutable. I can change values in them. That's what I did just here. I set the value. So let's do a tuple equals, okay, and let's try changing the value inside a tuple. Let's do sub0 equals 33. And we get an error. Boom. Isn't that awesome? And, it's important to talk about errors. I mean, legitimately in programming, when you get good at it, you spend 5% of your time writing code and 95% of your time fixing errors. So, in any kind of a system that you want to get good at or you want to improve, it's never the 5% that causes the problem. It's the 95%. If you can cut the 95% in half, you've doubled your productivity almost. So, let's talk about errors. Okay? The first one and the most important is you're not going to break the computer by producing an error. And that may seem silly to you, but if you deal with people at all, that especially the older generation like me, they're always afraid that they're going to type something in and break the computer. In fact, relative to computer programs, the computer is basically not very fragile. It's been designed, and a lot of effort has gone into the operating system and how it works to isolate your program from everything else that's going on your computer so it won't break. Now, there are things you can do to break the computer. Do not pour a beer into your computer. I have done that. That will kill the computer. I absolutely guarantee you that is the end. Okay, you will buy a new computer. But the software won't break it. Now, here's one for you. I'm going to tell you that errors are good. Let me repeat that. Errors are good. Okay, let me explain the details. First of all, a quote from Hirohito Honda, the head of Honda Motor Company and founder. And his point is that success is a matter of finding the exceptions to the errors. If my managers are not making 10 errors a day, then they're not doing enough. Now, what he's trying to say here is that you can control the rate at which you produce the errors. You can control the rate at which you get to the errors. You can control the productivity not by only doing the stuff that works, but by increasing the amount of stuff you do and finding the exceptions to the errors. If you want to program quicker, what you want to do is you want to get to the errors faster so that you can fix them sooner, so that you can move on to the next thing. That means that your goal should be, okay, let's put in some code and let's generate errors. Let's find the syntax errors, let's find the logical errors, let's find where you made the mistakes. That's your goal. It's not to write perfect programs. People that spend time grunging through, trying to produce in their head the perfect program, they don't produce much code. And there are a lot of people like that. So, making mistakes is scary, and it's against what you're taught in most of the school system. You're taught you're supposed to do it perfectly, that you're supposed to have the right answer. That's not the way software works. That's not the way business works. If you want to build a business, what you're trying to do is you're trying to get to the customers and find out what they really need and make the mistakes as quickly as possible so you can fix them and get past them. And success in business most often is just avoiding enough really stupid mistakes that you get to be successful. If you can avoid really idiotic things, then you make other errors and you recover and you move on. Now let's get back to tuples. So in any case, you notice that when I tried to change a value in my tuple, Python said, nope, that's an error. You can't do that because that kind of an object, a tuple, does not support item assignment. You can't go and change it. Now, I can go and change the whole tuple. I can say t equals 5, 6, and it's perfectly happy with that. I can now print out t and, not print 5. Print t, there's an error. I made one real quick and moved on. And you see it's 5, 6. So I can go and, change the entire tuple, but once I've created it, it's fixed. This is called immutable. And you can't change it, you can't mutate it, you can't tweak what's inside it. It's immutable. All right, so why would you want immutable data? Well, in the homework, we're going to read in a list, which is mutable, of tuples, which are immutable. So we've got name and phone number pairs, and you don't really want any reason why you would need to change your name. That's not up to the program. You go to a court to change your name when you get married or other reasons, but that's how you change your name. Nor is it up to the program when you're searching for a phone number to change the phone number. So we can prevent a class of errors by using a tuple instead of a list, because we can't assign to the wrong thing. And when I can prevent errors, I'm kind of keen on that, okay? Especially when I can get help from the programming language. So that is kind of the intro to this in terms of tuples and lists. Next, we're going to take a look at the actual code, and we're going to walk through that code. And I'm giving you this code. I expect you to use it. So there is this piece of the code, which has some stuff you have not seen before, and I understand that. Specifically, it goes and it reads in a file, this phone book file. And there's some syntax with how you read in a file, and then it creates this comma-separated value reader so that it can read in the entire file into this list of tuples. And that's what we're after, is we get to that list of tuples. I'm just giving you this read code. And this is one of those patterns. We talked about it before, but one more time, it's a pattern. You set up some stuff, you read some data, and then you're going to process the data, and then you're going to search through the data to find something. So in this case, we don't have any processing of the data. We just go straight to the search because there's nothing really that we needed to search. Now, there might be some reasons later why we need to search, but we aren't going to be talking about them right now. And then down here at the bottom, we have our search. That's this piece, lines 19 through 21. Basically go through every single piece of data one at a time for RR and list of tuples, and RR becomes each successive tuple in turn, and RR sub 0 is the name, and that's what we want to match. See if it is equal to the one we're looking for, which is my name, and when you find it, if you find it, print it out. Now there's a piece missing here. It doesn't print out an error message that it didn't find anything, but it gives you a search. If it returns nothing, you know it didn't find it. If I'm in there in the list 5 times, it's going to print it out 5 times. So this is not the most efficient way, but here's the code and the walkthrough. There's a whole bunch of stuff here, lines 5 through basically 15. That is the read portion. Now, we're going to test it on a little case with phone book being, I think, 4 entries. So when we come down to this list, it's just going to go through around and around 4 times. Then I'm going to give you a phone book that's much larger called Big Book that has, I think, 10,000 or 1,000 names in it and phone numbers. They're not real phone numbers, don't call them. Except mine, it's the only real phone number in there. And we're going to do the same search in that bigger list and see what we find. But basically, by testing on a small set, suddenly we can jump to a big set of data. And it wouldn't really matter except for how long it takes to run this, which set of data it's running, because basically the code is the same. We didn't change the code, we just changed the data we put into it. And that is a huge amount of power to be able to say, I'm going to test a certain set of fixed cases, a subset of what's out there. But I've made certain that there's an example of each case, And when I make certain that I've got examples that are thorough, that I go through and test, then I can turn around and I can suddenly jump from that to, okay, I expect this to work all the time on every kind of set of data like this, from 1 to 100 million or a billion rows of data, and expect the same code to perform in the same way. It's just more data that we're looking at.